happy to be here today. So my name is Benjamin Klausing. I'm the substitute for Dr. Thomas Jäger today. I'm project director at Tractebel GKW and deputy department head for industrial water management department at Tractebel. So today I would like to show you something that we did in the past, which is a project which was not just limited to engineering, but also provided as a turnkey solution to our client. So this project is mainly started with our client, which is a mold factory. They came to us with a really big problem. So they were intending to increase their production capacities, but during negotiations with the authorities, these authorities told them that it's not possible to increase the water consumption by the factory, since the availability of fresh water was limited. And at the same time, the plant was also not allowed to increase the amount of water to be discharged into the local sewer. So these were two main driving forces that were limiting their intentions to increase the production capacities. And therefore, they asked us to find a solution, what we can do to help them to increase production without increasing water demand and wastewater for discharge. So what we did is we did not just implement, for example, a reverse osmosis process in the end of the whole water process within the plant, but we first investigated what is the malting process itself, and maybe we tried to find out if maybe there's a better way of how to handle the water problem. So what we firstly did is within the malting process, it all starts with a grain of barley. So the barley is delivered to the plant. Then it's firstly sorted and cleaned from impurities, and then the pure barley is stored in a warehouse from where a steeping procedure is fed. Steeping means that you put the barley grains into a big vessel where it is flooded with water and allowed to fully soak with water. And after that, the water, after a certain period of time, the water is discharged from the steeping vessel. And this means here we got some effluent which is produced in high quantities, but in very short time spans. After that, the soaked material is then put into a germination chamber where the environmental conditions are controlled, such as temperature, for example. So in the germination chamber, the material starts to grow, which is called germination. And after a certain period of time, and the exact period of time is secret to all the different malting companies, so they all got a slightly different recipe for that. After a certain period of time, the germination process is stopped, and this is achieved by drying the material using hot air. So after drying the material, the germs and the grain itself is separated from each other, and the malt grains are then stored in warehouse buffer tanks from where it can be distributed to the different clients, which are, for example, breweries, distilleries, and so on. So while investigating this process, we quite early we found out that the huge water demand is existing in the steeping process, and that the effluent caused from the steeping process is only slightly polluted, which is mainly organic nature. And therefore we decided to go with a so-called membrane bioreactor process. And our intention was to take the effluent from the steeping process, to upgrade it so that we can use it in the steeping process again. And therefore this membrane bioreactor process is quite good opportunity. So what is a membrane bioreactor? So it mainly consists of two main components. The first one is the bioreactor, which is in the end just an open tank containing aeration facilities, containing the biomass, the bacteria which consume the impurities and all the stuff that comes with the effluent. And after that, there's a second stage of treatment, which is the membrane. And therefore, you got different options of membranes that you can use. For our purpose, what we want to do is we want to filter out the bacteria from the bioreactor and put the bacteria back into the process, and only allow a high quality permeate to be recycled into the steeping process. So therefore, we also decided not to go with a reverse osmosis, but to go with an ultrafiltration membrane, which is less energy consuming, at the same time not providing as high water quality as a reverse osmosis would do, but allowing us to still provide quite good water quality, which is sufficient for the production process. At the same time, ultrafiltration membranes are not reducing salt concentrations. I think this is important to mention. This is why we are also monitoring salt concentrations in the whole process, because we don't want to increase salt concentrations by recycling the water. So this is something that we have to keep an eye on. So what's the different concept or the difference between conventional wastewater treatment plants and the membrane bioreactor process? As you can see, conventional process is also comprising a bioreactor, but the bacteria, all the biomass is removed from the process by a settling tank, by a vessel, which is consuming, consuming huge volumes and also a huge footprint. For the membrane bioreactor process, we also got the bioreactor, but we use the membrane, which consumes less surface, which is less footprint in the end. And by highly efficient membranes recycling the bacteria back into the bioreactor, we can also increase the concentration of bacteria in the bioreactor, causing or allowing us to reduce the volume and therefore the footprint of the bioreactor itself as well. So integrated into the mold plant process, the concept looks more or less like this. So we're taking the wastewater from the steeping process, and then we route it firstly into a buffer tank. And this is very important. As I already mentioned, we are creating high flow rates of effluent in very short times. Therefore, we uncouple the production of effluent from the treatment of effluent, allowing us more treatment times and downsizing of the plant equipment. From this buffer tank, first step is a screening where we take out impurities such as sand, gravel, or some leaves which might have fallen into the buffer tank and stuff like that. After the screening, the effluent is routed into the biology tank, and from there the bacteria are filtered out via the ultrafiltration process. The bacteria are rerouted into the biology, and the permeate, which is the recycling water, is then stored in a very huge buffer tank and provided to the mold factory. For sanitary reasons, we also add some agents for disinfection, just to make sure that everything is in a good quality condition. But after the ultrafiltration process, the quality of the water is already really good. Since the biology also creates additional biomass due to the nature of the bacteria, we also have to take care of that. And we do it by extracting certain amounts of filling from the biology and putting it into a small buffer tank. And from there on, we are feeding a sludge dewatering unit. And the sludge dewatering unit now provides us with a dry material, a solid material, which we are then feeding as a substrate into a local biogas plant for energy recovery. And the really good news is that the digestate from the biogas plant is then also used as fertilizer on the fields where the grains for the mold production are growing. So we are also able to close nutrient cycles by this way of treatment. Here I got some impressions on how the plant looks like. On the left side, you can see the recycling buffer tank, which is comes with a capacity of approximately 800 cubic meters. In the center, you can see the image of our main components of the treatment plant. The lower container contains the ultrafiltration process and also some electrical cabinets and a control room. The upper container contains the dewatering facilities and also the tanks, which are relevant for that. And on the left side on this slide, you can see this is the condition of the dewatered sludge as we get it from the sludge dewatering process. And on the right hand, you can see the biogas plant, which then utilizes this dry sludge as nutrient and also as substrate. Okay, I also already put my finger on the hygienic conditions. So we also did tests on that. So the permeate was tested. The first test, as you can see, comprising the colony forming units at 36 degrees of Celsius. You can see the first sample, there were still some colony forming uses noticeable. Then we optimized the addition of hygienics of sodium hypochlorite. And then you can see the second and the third sample, the the bacteria concentration, so the concentration of the colony forming units was drastically reduced. And so we also have a very hygiene water that we can use for production processes. So what are the benefits for our clients? So there are three main benefits. The first one is we are saving, due to implementation of this plant, roughly 170 tons of carbon dioxide every year. And also we are recycling 180,000 cubic meters of water every year. And also on the economical side, this corresponds to roughly 400,000 euros every year, which our client can save due to not buying water or less water from the grid and not having to discharge and pay for the treatment of the water in the local sewer.
2 minutes, Benjamin.
Okay. Yeah, so this is already my last slide. So just to summarize what we did, first thing was we did not just come up with a solution, but firstly, we had a deeper dive into the production process itself and identified that the steeping step is the main driving force and the best option to gain wastewater or effluent for recycling. And we decided to go with a so-called membrane bioreactor stage, which combines an biological treatment with an ultrafiltration retention for the bacteria. The biomass that we gain from the treatment is then utilized in a local biogas plant, which is very close to the malt factory. So we're just talking about 3 kilometers. And yeah, the good news is the biogas plant is then recovering the energy by producing biogas, but also the nutritions can be utilized by using the digestate from the biogas plant as biofertilizer on the fields where the grains used for malt production are cultivated. Okay, thank you very much.
Okay, that is the presentation, Mr. Benjamin. Thank you. Thank you very much.